Everyone.
Oh, it's not that actually.
Hello, everyone. Good morning,
Thank you.
good afternoon, good evening. Thank you very much for giving me this opportunity to talk about my PhD. I'm Moein Mellat. I'm a first-year PhD student at Alfred Wegener Institute in Germany. And in this project, I'm collaborating with Hanna Maya, Martin Werner, and Camilla Brunello. In the next 10 minutes, I want to talk about the isotopic traits of the Arctic water cycle. So first, we face the question, why Arctic? As you can see here in this plot and the animation, Arctic has experienced surface air temperature increase at a pace twice the global rate during the past decades, and a severe increase in sea ice extent and the age of it as an outcome. So we studied the changing Arctic to understand the consequences on the hydrological cycle in the future. But along the way, we face a reality, and the reality is that there is lack of observational data, specifically during winter time. The main reason for this paucity of data could be that the sample and data collection from remote and frozen Arctic has always been challenging. This brings us to the importance of MOSAIC expedition, where scientists from Alfred Wegener Institute planned for many years to have one full year in the Arctic. This expedition finally took place between September 2019 to September 2020 in collaboration with colleagues from many other countries. And the German research vessel Polarstern broke into the ice and got trapped in the ice in an area north of Siberia and Laptev Sea. And it was then driven by the transpolar drift on the ice flow, and that naturally moved towards Farm Strait. Along the way, scientists from different disciplines had the opportunity to have in situ observations and sample collections to investigate the climate processes that couple the atmosphere, ocean, and seawater, sea ice. These efforts basically provided us with the opportunity for our project, Kiasom. And in this project, we take a look into the changes of Arctic, as shown here on this picture, and different water compartments, interactions, and the isotopic imprint of them on one another was the main question in mind starting this project. And since no one from our project, the people that I mentioned, have been present during the MOSAIC on Polarstern, our study basically relied on the efforts of other scientists. And because of that, I also had to spend some time gathering the information and getting familiar with different sampling campaigns on the ice flow. And mainly the overarching goals of the project are first to have the first comprehensive description of isotopic composition of the Arctic for the full complete annual year, including understudied winter. Also to have an evaluation of key sea ice, ocean, and atmospheric exchange processes and the impact they have on the Arctic water isotopes, and to finally see that imprint that sea ice conditions leave on the isotopic signature of the Arctic water and the way they're represented in the coastal Panarctic stations. So we had the total number of 2,082 samples, and the timeline of different legs with the numbers, you can find them at the bottom here, with the dates of different legs or parts of the expedition that I'm going to refer to as legs from here on. So what are these different main compartments that are shaping the Arctic water cycle? Let's start with snow. In this illustration, I will go through all of these. Let's start with snow, which is deposited on top of the sea ice, and that was the samples that our colleagues collected. We have also some frost flower samples, which are basically just crystals of ice that form when water vapor becomes solid by bypassing the liquid phase and deposits on the young sea ice surface. And then we had the melt ponds, which appeared during warmer months in summer when the sea ice started to melt on the top. Also, there were leads, which are basically the cracks formed by the winds, tides, and currents in the Arctic. And then the seawater comes up to the surface in between these parts of ice. The sea ice also was another compartment, which is here categorized into first-year ice or younger ice that has been formed during the same winter, and second-year ice, which is thicker and older than first-year ice and has survived from completely melting out during at least one summer. And seawater was collected on a daily basis from the underneath of Polarstern at the depth of 2 meters. And here I deal with these discrete samples in my PhD project, and my colleague Camilla Brunello focuses on continuous vapor data measured by the Picaro on board of Polarstern during the full 1 year. So we gathered these samples from our colleagues who had sampled them, and here in an overview of our measurements at Isotope Laboratory at Alfred Wegener Institute in Potsdam. You can see the measurements. We deal with a wide range of delta 18O values, with having the snow as the most depleted compartment, down to seawater and first-year ice as the most enriched ones. In the next slides, I will go through the analytical results of these discrete sampling. So first on a co-isotope plot, I will show that. And here I have used a global meteoric water line just as a reference to see how different sample types plot around this line, although I know that these samples are not really meteoric samples by definition, and not all of them at least. So first with the snow, we observed the most depleted values in the snow, and they were also the most variable, and they had the most variable isotopic signatures. Frost flowers also had the signature similar to snow, but with way less samples taken, with only 10 samples taken opportunistically. And then going from the most depleted to the most enriched value that we have seen in delta 18O was the seawater. And then we moving towards the ice. So with the first-year ice samples, we can see a possible mixture of the snow with the sea ice with the lower delta 18O values of some of these samples. Second-year ice was basically a bit more depleted as it was older, and it plots on the upper side of the plot, but with values between 0 and -10. And then there was rafted ice, which basically was a mixture of the two and plots over first-year ice and second-year ice co-isotopes. Meltwater layer of ponds had a wider range of more depleted isotope values compared to seawater, which was plotting just on the upper scale of this line. And finally, lead samples and lead isotopes plot mainly on the upper part of the line, with a few samples with snow signature, as you can see here, down to -15. So to have another look at the comparison of these values, on the right plot here, we can see the distribution of delta 18O and d-axis values. D-axis here is presented in orange color, and we see that snow and frost flower have have more positive values of d-axis, while other compartments are mainly spread around 0 per mil for d-axis. So this could be partly due to the atmospheric source of snow and frost flower samples compared to the other probably seawater source samples here. Although many outliers we can see with the snow samples with many negative values, and with the lead samples both negative and positive, and first-year ice d-axis with some more positive values as outliers. Now I want to have brief discussions about 2 of these sample types, seawater and snow, in the next few slides. So first, let's take a step back and take a look at the MOSAIC track. So the continuous blue line here represents the continuous legs of 1, 2, and 3 from October 2019 to May 2020. After a break in Svalbard, leg 4 took place for around 6 weeks during June and July to 2020 in the Fram Strait corridor. And then the last part of the expedition, shown as red here, for that part, Polarstern went up close to the North Pole for around 4 weeks in August and September 2020. So the seawater delta 18O was variable throughout the year at different locations as well. And it basically ranged from plus 0.5 down to minus 3.5 per mil, with different water sources from Atlantic Ocean currents to freshwater release into the Arctic, and also the sea ice melt imprint, sea ice melt water imprint, attributing to isotopic composition of seawater in the Arctic. These measurements can be better interpreted based on variable sources when looking at the salinity of seawater in the Arctic. So here we see that when Polarstern was passing through the parts of the Arctic Ocean with more saline water, which is represented as more green colors here, delta 18O values were higher compared to the times that the samples were collected at less saline areas in the Arctic, which is represented more with the orange colors. Here we take a closer look specifically at the case of leg 4. It's interesting that at around 0 degree longitude, the isotope values start to drop progressively. So on the right side of 0 degree longitude, it seems that Atlantic water is entering the Arctic, while on the left, where Polarstern was again moving on the ice flow, Arctic Ocean sea ice and seawater were being released towards the Atlantic. It can be also observed by taking a look at time series of seawater delta 18O, salinity, vapor delta 18O, and air temperature. So seawater and salinity here on the top, their time series, on one hand, and also vapor and air temperature down here on the other hand, have the same trend. During leg 4, vapor is getting progressively enriched, probably under the influence of Atlantic moisture. At the same time, seawater isotopic depletion was more influenced by the sea ice release from the Arctic towards the Atlantic. Vapor time series here has been just discussed, in detail in the poster presentation of my colleague Camilla, that you can attend later today. So let's talk about.
Please conclude soon.
Yeah. Only 1 minute. Yeah.
1 minute.
Yeah. I present the time series of dx's and delta 18O values for the sea ice at the top centimeters and bottom layer and top layer of snow. So here we can see a clear offset between top and bottom layers of snow here at delta 18O, which gives us the potential processes in place such as sublimation of deposited snow by the time. And then there is a mixture of bottom layer of snow with the sea ice, which is apparent more between October to May here that we can see, but also with dx's. The dx's for sea ice, top sea ice level is around 0, but we can see that the bottom layer of snow drops even further below 0, and that's a really interesting observation from the top to the bottom. So just to put it in a nutshell, MOSAIC expedition provided a unique opportunity to have this first-hand isotope data set, and seawater isotopes get progressively depleted as Polarstern moves towards less saline water. So the question is, what is the origin of this depleted water? And then fresh snow layering on top of the sea ice displays a progressive enrichment from surface to bottom. So can we disentangle post-depositional metamorphic processes? Thank you very much for giving me this opportunity, and I would also like to thank the colleagues that provided us with this great data set. You can see their names here, and I would be happy to be in touch with you for further discussion and talking about isotopes in the Arctic. Thank you very much.